Okay students, welcome to MRP classes. We will continue the discussion of thermodynamics. Today, let us go to one of the important topics from thermodynamics, that is entropy change. Entropy change. What is entropy? What is entropy? Entropy, it is the measure of randomness or possibilities or freedom or options in the system. Okay. Imagine, we know that gas, liquid, solid, entropy increases. We know this. How do you justify this definition here? Suppose a substance in gas. Here. But actually, solid, liquid, and gas. Entropy increases. Suppose a particle in the solid state. It is very closely packed. Therefore, the freedom of motion is very limited. When it moves from solid to liquid, freedom of motion increased. From liquid to gas, again it is increased. That is why entropy increased. Now you suppose you mixing A and B. A is sugar, B is water. You get AP solution. In the case of sugar alone, molecules have only the connections with the sugar molecules. There is only sugar connection. There is only water connection here. But when you mix, more options of connection. There will be sugar, water, sugar, water. Fine. That is why towards entropy increased. Therefore, every process where the freedom, randomness, possibilities, options increase, that change will accompany with an increase in entropy. Imagine you are sitting in a class with a very strict teacher's class. You are sitting in a strict teacher's class. Very strict teacher. You can't look at your friend. You can't turn back to your friend. You can't look at outside. Only look at the teacher. Look at the board. Listen to the teacher. These are the only options. Okay? Imagine teacher leave the class. Just for a moment, teacher leave the class. What is the nature of the class? Spontaneously, class will burst into more options, more freedoms. Therefore, this is a process where entropy increased. Okay. Therefore, entropy increasing means in that system, more options are found, more options are obtaining. Now the entropy change is calculated by dQ by T. What is dQ? Or Q by T? I said Q is heat liberated or absorbed at a given temperature. Now this Q may be heat liberated or absorbed during the process. Normally at pressure QP, that is delta H. Therefore, entropy change can be represented by like this. Okay? Or it can be represented by delta Cp delta T by T. Okay. We know that Cp delta T because delta H is equal to Cp delta T. We know this. Okay. Now in this process, suppose delta S for melting Delta S for melting is delta H melting by T. Here the unit of entropy is equal to joule per Kelvin. Therefore, it should be into 10 raised to 3 joule. This should be Kelvin. Very careful that. Because entropy of, unit of entropy is always joule per Kelvin. Now, delta S vaporization. Delta H vaporization by boiling temperature at Kelvin. Here melting point. Here also 10 raised to 3 joule. Now delta H sublimation. Delta H sublimation into 10 raised to 3 joule. If it is given in kilojoule. Okay. If it is given in kilojoule. Sublimation temperature. Kelvin. 10 raised to 3 should be multiplied if it is given in kilojoule. Remember. If it is given in kilojoule. If it is kilojoule. If it is kilojoule, make it joule. That's very important. Because unit of entropy is always fixed. Joule per Kelvin. Now another option. Now delta S is equal to, we said you delta S is equal to Q by T. Delta S is equal to Q by T. Sorry. Q is equal to, we know that delta E is equal to Q minus P delta V, like that. Therefore, Q is equal to delta E plus P delta V by T. Okay, delta S is equal to delta E by T plus P delta V by T. Delta E means CV delta T by T plus, for an ideal gas, PD is equal to nRT. Here NCV for 1 mole, for n mole. Therefore, T is equal to nRT by V. Therefore, instead of P, I use nRT by V into T delta V. Instead of P, what I use? T and T cancelled. Therefore, delta S is equal to NCV delta T by T plus NR delta V by V. On integration, therefore, now you remember this, very, very important. Now please remember, from this equation, you remember following equations for numericals. Delta S is equal, okay? Yes. Now for an ideal gas, delta S is equal to NCV 2.303 log T2 by T1. NCV delta T by T, you remember that? Yes. Plus NR log 2.303 log V2 by V1 for solving the numericals. RL delta S is equal to NCV 2.303 log T2 by T1 plus NR 2.303 log P1 by P2. Okay? Yes. Now delta S is equal to, here V2 by V1, P1 by P2. You know that. Now delta S for isochoric. For an isochoric, this word 0. Therefore, NCV 2.303 log T2 by T1. Delta S isobaric, this term, okay? Therefore, NCV ln T2 by T1 into 2.303 for solving the numericals, okay? Ln, whatever you get, multiply with 2. I just give you the equation in different forms. Isobaric. Now delta S, isochoric, isobaric. Now delta S isothermal. Isothermal. Isothermal means you can use this equation of the, anyway this word is 0, this word is 0. You can use either this, that is nr ln V2 by V1 into 2.303 or nr ln P1 by P2 into 2.303. 2.303. Okay. Here volume C, here pressure. Now delta S, very adiabatic. Adiabatic. Yes. For an adiabatic, delta S is equal to 0. Very important. Because delta fundamental equation is equal to Q by T. For an adiabatic, this is 0. 0 by T is equal to 0. Okay? Yes. Therefore, these are the equations for our entropy change calculations. One minute. Okay. I got it. These are our equations. Sublimation, delta H sublimation divided by sublimation temperature. Sublimation temperature Kelvin, Joule. Delta S melting. Delta H melting divided by melting point Kelvin, Joule. Now, delta S for ideal gas, NCV ln T2 by T1 plus NR ln V2 by V1 ln is equal to 2.303 log or NCV ln T2 by T1 plus NR ln P1 by P2. Isothermal, these terms are zeros. Isothermal. Okay. Isochoric, this term is 0. Isobaric, this term is 0. Adiabatic, Q is equal to 0, delta S is equal to 0. Very simple. Okay. Now we can solve some question. Okay, identify the entropy change of these processes. Identify the entropy change of this process. Here, SOCl2 gas become SO2 gas and Cl2 gas. Here delta is positive because here 2 gas, here only 1 mole gas. Here it is a gas, n moles of this become polymer. Here delta is negative because gas become polymer, solid. Here gas becomes solid. but here gas become more gaseous. Here iodine, this is solid iodine, this is gaseous iodine. Therefore solid to gas, delta S positive. Here reversible, adiabatic reversible process. For adiabatic process, delta S is equal to 0. Therefore this is the question. You have to match, you can match it very simply. Now you can go to next question. Okay. Are you okay? Yes. 1 mole of an ideal gas initially at 300 Kelvin at a pressure of 10 atm undergoes a adiabatic expansion reversibly, second, irreversibly against a constant external pressure of 2 atm until the final pressure becomes equal to external pressure. Calculate delta S for both systems. Okay? Calculate the entropy change of both cases. That is 1 mole of an ideal gas initially at 300 Kelvin and at a pressure of 10 atm undergoes adiabatic expansion reversibly and irreversibly. In a reversible adiabatic expansion, that is delta S is equal to Q reverse by T. For a reversible, Q reverse is equal to 0. Therefore, in this case it is 0. No more calculation. Adiabatic reversible. But irreversibly against a constant external pressure, 2 atm, until the final pressure become equal to external pressure. Therefore, P1 is equal to 10 atm, P2 is equal to 2 atm. Okay? Expanded until external pressure of become 2 atm. Okay? Fine. Therefore, pressure is changing. Ideal gas initially at 300 Kelvin. Okay. Therefore, it is very lengthy problem. Listen here. Which equation? Ideal gas equation. P1 is 10 atm, P2 is equal to 2 atm, T1 is equal to at 300, T2. Is it isothermal? No. Question does not tell you that the reaction is isothermal. Therefore, For an ideal gas, general equation is equal to NCV ln T2 by T1 plus NR ln P1 by P2. Okay, the ln should be converted into logarithm by multiplying 2.303. But the problem, you don't know the T2. If there was a term isothermal, we were lucky. We can neglect this part, but here we can't do, because question does not tell you it is isothermal. Therefore, we use this. We want to find out T2, and we have to do this part also. Therefore, first, N is 1 mole. Okay, no problem. R we know, CV. I'm sorry, CV also given. Okay, we will let CV also given in the question. Okay, we find out the T2 first. Okay, how to find out T2? Yes, we know this equation. Delta U is equal to Q minus PD. Delta U is equal to CV. Delta U is equal to CV delta T. Therefore, CV delta T is equal to Q minus PD. For an adiabatic process, whether it is reversible or irreversible, we can say that Q is equal to 0. Therefore, CV delta T is equal to minus P delta V. Or CV delta T plus P delta V is equal to 0. CV into T2 minus T1. In the case of a P is equal to nRT for 1 mole, RT by V. Am I correct? Okay. Or plus P into V2 minus V1 delta V. V is equal to RT by P. Therefore, V2 is equal to RT2 by P2. V1 is equal to RT1 by P1. Okay. Therefore, I write like this: CV into T2 minus T1 is plus P into RT2 by P2 minus RT1 by P1. Okay. Okay. Now our aim is, for an ideal gas, monatomic CV, they are given CV as 3 by 2 R. Therefore, we will 3 by 2 R T2 minus 300 plus P external pressure, that is 2 into R. This P is external pressure, okay? R T2 divided by P2 is 2 minus R taken out 300 divided by 10. Now our aim is, I am not going to detail of this problem, find out T2 first. Get the T2 here and apply T2 here. This is 3 by 2 R. N is equal to 1 mole. Apply that T2 here. Okay, we will get the final answer. Now we can go to the next question. when 100 gram of water is reversibly heated from 50 degrees centigrade to 75 degrees centigrade at 1 atm. What is the change in delta S of the universe? Change in entropy of the universe, not the system. That's a very important question. Whatever the value you got, that opposite value will be the universe. Okay, we will solve that question. 100 gram of water heated from this. Heated from this temperature to this at 1 atm. Therefore, it is isobaric. We are very lucky. Isobaric. Therefore, delta S is equal to NCV ln T2 by T1 because isobaric. T1 is equal to 50. T2 is equal to 75 plus 273 plus 273. Water CV, here CV is specific heat capacity CV. For water in joule, the value of in joule is equal to 4.2 joule per Kelvin. 1 calorie per Kelvin or joule, in terms of joule, this is the value CV. Therefore, 100 gram of water means number of moles is equal to 100 by 18 into 4.2 into 2.303 into log 348 divided by 320. Delta S, after the calculation you will get 31.3 joule per Kelvin. This is the entropy change associated with water. It's a positive value. Okay, you got the positive value. So it is entropy of system. Therefore, that of surrounding is equal to minus 31.3 joule per Kelvin. Okay, surrounding is this. Because it is a reversible process. Reversible. The reversible heating. Reversible means very slow process. There is a reverse back. Whatever the system achieved, that can be reverted back. Therefore, if there is this much entropy increase in the system, since it is reversible, that much will be decreased in the surrounding. Okay. Normally, entropy, we will use a word delta S total. Delta S total means delta S system plus delta S surrounding. For a reversible or equilibrium, reversible or equilibrium, delta S total is equal to 0. You know why? In this example, here 31.1, it should be minus 31. For a reversible or equilibrium system delta S total is equal to 0. For irreversible or non-equilibrium system, delta S total not equal to 0. Therefore, this value not equal to this value. Therefore, why we take exactly negative? Because of the word reversible in the question or equilibrium in the question. Otherwise, you don't take that. Okay? Yes. Thank you for watching. If you find any difficulty, let us discuss in the comment box. Okay? Thank you.